The one of the talk will not be presented because we have a small problem with computer. So what we'll do next is to present, in fact, the last presentation of the morning. And this one is a little, let's say, introduction about what will come next in terms of process simulation in FactSage. So I will share my screen and I'll start this presentation in a moment. So share. It's good. Screen number 2. In theory, Ev, you should be able to see my screen. That's good.
Yes.
Perfect. So let's go with the next presentation, which is on handling streams and multiple equilibrium reactor in FactSage. So we have many experienced customers here that are with us today. So maybe we can get some of their feedback after this presentation. And if they are enjoying what they're seeing, can put a little bit of pressure on Chris and Arthur to see this feature in FactSage as soon as possible. Okay, so the topic of discussion in this talk will be about trying to model processes on a mass and energy balance perspective. So what I want to do now is to focus on this simple example, which is, I would say, a conventional example that we want to deal usually when we are trying to simulate a process, which to have a first unit operation. So in this case, for example, we'll have direct reduction at 900 degrees Celsius. Then we would like to use the product that we obtained from this reactor. Maybe the gas phase will be removed from the system, and we'll then try to use these condensed phase, maybe react them with another reducing agent in this case to continue the reduction or alloying it with another element, and this would take place in another unit. So basically, the example that I will work on is the reduction of hematite, and I'll use 2 reducing agents to do so. So the first one will be CO at a temperature of 900 degrees Celsius, and the next unit will be at 1600 degrees Celsius with 5 kilograms of graphite. Okay, some important aspect to mention here. This is not modeling a real-life process. It's just a theoretical example. First of all, the second thing is that you see here the presence of graphite. Typically, in pyrometallurgical operation, we would use coke, but as you know, coke is not an equilibrium phase, so we would need to describe and characterize the energetics of this coke material. And since we wanted just to focus on the handling of the stream, I will assume here that we're using graphite. I'll do the same thing in the afternoon when I deal with the carbo reduction of hematite again. So in this example, what I would like to do is to introduce in my first unit 10 kg per hour of CO, and I would like to react it with 10 kg of Fe2O3. Of course, knowing the metallurgy of the system, we would probably produce some austenite, some austenite or some ferrite, depending on the temperature of operation, so FCC or BCC iron. If I don't have enough CO, then I will end up with some FeO remaining in my system. And of course, there will be a gas where the oxygen and carbon will be removed from the system. So typically what you would like to do is to start with this reactor, perform a first equilibrium calculation. Then you would save some stream that you are interested in. In this case, for this specific example, I want to see the fate of FeO and FCC in my second unit operation, which will be operated at a different temperature, a much higher temperature. In this case, again, it is not a real process, but I'm using the temperature that is typically used in a blast furnace or in a high temperature electric arc furnace. And of course, wanted to analyze what would be the end up results. What we face as a user when we try to simulate this are multiple challenges. First, we need to do this sequentially. So you would start with unit number 1, save the stream, solve the reactor number 2. And the problem here is that if you add a level of complexity in the feed, or if you change one of the variable, then you have to do the process again, which is time consuming. Even sometimes it's difficult to follow which stream have been saved or which stream to use. So let's use this example and let's move on toward the first simulation that we would do in Equilib. So I just focus here on unit number 1. So you would go in Equilib, put the input amount of CO and Fe2O3. Depending on the fact that you want or not the energy balance to be solved, you would activate or not the initial condition. Then you would go in the data search and activate the important database that you want to use for this specific example. In this case, I would activate FT oxide, FS-steel, and FactPS. You will see in the afternoon we always are activating the FactPS database, and this is for a good reason, because this is the only database that contains all the thermodynamic information about the gaseous species that we have available to the user. So we always activate this FactPS database, and we also have the FS-steel and FT oxide to represent the behavior of the oxide component or the oxide phases that may form, as well as the phases that are typically present in a steel. So that's the first step you would do. Then you would calculate the result, and it will take some time, and you would analyze these results. So as I suspected, because I've run this example many times and I'm aware of what is happening in the system, I guess right. So there is a gas phase forming, mostly CO and CO2. So we don't have enough carbon in our system, so this is an indication that there will not be complete reduction. We have a monoxide phase, which mainly contains FeO. So you see here that we were able to partially reduce iron, and we have some iron also forming. So unfortunately, in this case, with the first guess I did of the amount of CO required for this amount of hematite, I still have an incomplete reduction process, and I need to further reduce the condense phase if I want to obtain metallic iron. So what would I need to do to go to the next step would be to save the stream, and we'll see that during the presentation this afternoon. So let's say that I'm interested in reacting FeO and Fe, the FCC solid solution. I would go in stream file, save stream, save solution, and I will browse down and select FT monoxide. I will give it a name, and I will be able to use it afterward. But don't forget that if you change the condition of the mass balance, you will have to redo that again and again. So it's time consuming, and it will bring a long list of streams to manage. So the second one, okay, the next step would be to go in streams, save stream file, and save solution. We'll go to the FCC, and then we'll be able to start our simulation. Hopefully, we have another option to ease the process a little, so we can recycle all the stream, and this will speed up a little bit the process. So if we want to keep everything, we can just recycle all stream, and will be sent to the mass balance window, where we can put zero amount of gas in the eventuality that we don't want to use the gas in our further calculation. So we have done that, we've done the calculation, we have saved the stream. Now we need to solve the equilibrium reactor. So we would go back in the mass balance window. We would, in this case, put 100% of the monoxide solid solution, 100% of the FCC solid solution, and we'll add another stream that contains carbon. We would continue and obtain the result by calculating the equilibrium state. And here you would see that we have some gas, a liquid, and under this condition, I put too much carbon, so I have an excess of carbon. I have a saturation of carbon in my liquid iron, and I would say, okay, now I'm not pleased with that. I would like to go back to the initial reactor number one, start again with a different amount of CO, and perform this again and again. So you can see that this is pretty time consuming, and there are many things that can be changed when we're doing this process simulation. We could change the feed input, we could change the operating temperature, so this is a tedious process, and when we want to change something, we'll spend a lot of time saving all these streams. So hopefully, I was lucky enough to have a super good student this summer, Evan Fortier, who is not with us today. All these students that you saw before at the bachelor level, they were kind enough to extend their internship to provide me with a really good presentation. So Evan is not with us, so I recorded. So I think you should lower a little bit your sound because I think it's pretty loud, this one. So you will see in action the new interface that we build to ease the process of ending stream and starting to simulate processes. So I'll stop my microphone and be aware it might be a little bit high. Okay, so like I just presented, it can be quite complicated to perform process simulation using the equilibrium module, especially when we have to deal with streams. So we are working right now on a solution to solve this problem, which is to build an interface that would allow us to do some kind of
The sound has stopped.
basic process simulation using the interface that we see on the screen now. So Evan built this interface and we'll try to use it. So basically the first step that we're going to explore today is to open a thermodynamic file, so a CST file that contains all the phases that may form at equilibrium. So now Evan will browse and open one of the CST file that we have saved already to perform this first example. So now the thermodynamic database is loaded and we will be able to use all these phases that may form at equilibrium selected from the equilibrium menu. So what I will try to do is to copy the exact same example I presented previously, which accounted for the presence of two equilibrium reactor and one splitter. So what Evan will do first is to drag and drop a reactor on this interface. So this reactor will definitely add some input stream to it and at least one output stream. So Evan will build two input stream. We're going to define the amount in a moment. And there will be one output stream coming out of this reactor. So this first reactor will be operated at a temperature of 900 degrees Celsius. So what we can do already is to change this temperature. So Evan can add a temperature of 900 degrees Celsius. So later on, when we're going to solve this flow sheet, we'll be able to use the right temperature. So that's good. You can close this. So now let's focus on this first reactor. And as we saw previously, I want to reduce hematite using carbon monoxide. So the first step will be to take the first stream and to impose the mass balance to this stream. So this stream will be entering the reactor at a temperature of 25 degrees Celsius. So now we have an interesting option to build this stream, and we can select the phases that will constitute this stream. So if you hit this button, you can see that we can either consider a monophasic stream or a multiphasic stream. In this case, I want a gas, so I want a solution, and I will add 10 kilogram per hour of CO. So I'll take the gas ideal, and in the component mass flow, I'm gonna set the amount of CO to a value of 10 kilogram per hour. So that's good. So now you can see that we have in this stream an ideal gas that contains 10 kilogram per hour, and it's CO that is available in the stream. So that's good. So now you will move to the next stream. So you're going to go to stream number 2. And we'll introduce hematite, so Fe2O3, at a temperature of 35 degrees Celsius. So please, Evan, just change the temperature. 35 degrees Celsius. So that's good. So now what we want is to add and build the stream. So the stream will be of hematite, so it's a stoichiometric compound, a monophasic stream. So you go and select phases, monophasic compound, and what we want is to select Fe2O3 hematite. So by scrolling down, you can find this Fe2O3 hematite, and what we want is 10 kilogram per hour of this hematite stream. That's good. So now we're almost ready to run a first simulation. So Evan can present that the reactor now is set. So if you look at the properties of this reactor, we can see that there are two streams coming in, one stream coming out. The temperature has been imposed, and we're ready to look at the result. So Evan now will solve the flow sheet. And when this task is performed, you can see that the arrows are becoming yellow. And we can look in the output stream what has been produced. So you see here, without any surprise, that there's a gas phase that is produced, and this gas phase will contain CO and CO2. So you can maybe browse down and see the amount of CO and CO2 that we have in the stream. So you see here that we have almost half of it which contain CO and CO2. So that's good. You can minimize this component mass flow. There's also iron FCC that is produced. So that's the second phase that you see here. So it mostly contains iron with some amount of carbon as well. So that's okay. You can minimize this. And finally, since we didn't use enough CO, there's still some iron that is not fully reduced. And you see that monoxide contains mostly FeO, as you can see here in the output result. So this is pretty good. Now what we want is to react these solid phases. So we want to use these condensed phase and react them with graphite. So what Ivan will do at the next stage is to add a splitter, because we want to separate the gas that is produced from the condensed phase, so the FCC and monoxide. So he's going to connect the output stream to a splitter. Then you can divide this in two output streams. So one will be the gas and the other one the condensed phase. So you're gonna bring the condensed phase to a second reactor. So please add another reactor, which will be operated at a temperature of 1600 degrees Celsius. So you can already define the temperature. So 1600 degrees Celsius, typically that will be the operating temperature of the blast furnace. So that's good. So we know it's the type of ideal condition for the reduction of iron at high temperature. So you're going to add to this second reactor another input stream, because now instead of CO, we're going to use graphite as the reducing agent. So unfortunately, as of now, we don't have a good description of coke in our database. So you're going to use graphite at a temperature of 200 degrees Celsius. So you're going to build this stream. So build is going to be a monophasic stream compound, and that will be graphite. So you select the graphite, and what we want is 5 kilograms per hour. Good. So by doing that, we are now able to continue. If we add an output stream to this reactor, we can complete this solving this flow sheet. So we can hit this button, and now we see that the last reactor and the splitter they have been solved, and we can look at the output results. So if you look in this output stream, we can see that there's a gas and a liquid iron produced, which contains some carbon in it. So that's our example number one. Now, if you look at these results, so can you come back to the results? So let's analyze these results. We see that there's also graphite at the top, so it means that we added too much carbon. So we saturated the liquid iron, and we have an excess of carbon. So now I want to show you a second iteration where I'm instead of using 5 kilogram, I will use only 1 kilogram of graphite. So you can close this, go back to the input stream where we added this this graphite, and instead of 5 kilogram, you're going to use 1 kilogram of graphite. Okay, so now that's good. You can easily now solve this flow sheet again, and you see that only a part of the complete flow sheet was not solved. Now it is solved, and if you look at the output result, you'll see that there's no more excess of carbon. So we use the right amount of graphite to reduce completely the monoxide that was left in our system, and we have some amount of carbon dissolved in the liquid iron. So that's perfect. And in the final example, what I want to show you is the flexibility of this interface. So let's assume now that we want to use less CO as a reducing agent. So now we're going to go back, so you can close this window. We're going to go back to the CO stream, and instead of using a value of 10 kilogram, we're going to lower this value to 5 kilogram per hour of CO. So that's good. And now you can see that we need to solve again the flow sheet. So you can do that. And we're going to analyze the result again. So you can start by looking at the intermediate output stream there. And what we can notice here is the fact that we're not producing any more iron. So the FCC phase is gone. Therefore, we don't have enough reducing gas to bring iron to its metallic state. So you can close that, and you will see the impact it will have on the final output result. So for the amount of carbon that we use, you can see at the end that in this case, we have a liquid iron with the presence of a slag phase. So this slag implies that we were not able to completely reduce the iron from Fe2O3. . Okay, so I guess sorry for the loud microphone because just a short story here. I'm still with my friend, my kids here, and you will see in the afternoon that my videos are quite calmer than that because I was recording while they were sleeping, and some of the students mentioned that the sound was too low in my recording, so I boosted a little bit too much my voice there. So you can see that we have a new.
For me, it wasn't too loud.
Okay, good. So anyway, what you can see is that we're working on, let's say, a small process simulator, but really just to ease the use and to add some flexibility to the regular calculation that we're doing FactSage. Hopefully, I saw a couple of comments in the chat. So if you want to see this feature in FactSage, perhaps not maybe 8.2, but if you are interested and you feel like it's a good idea, maybe by sending this email to Chris and Arthur, we'll speed up the process because I think we're almost ready to have something interesting for our client. And maybe a couple of emails will ease, let's say, the introduction of this interface in FactSage 8.2, who knows? Okay, so I think that's the end of our discussion for this morning. I hope you enjoyed it. Again, let me try to see if there are still people connected, so that's good. I think we were able to maintain a core during our presentations. I'm quite pleased about that. And maybe we can virtually upload all our students who I think did a fantastic job this morning. To be honest with you, it's above my expectation. I'm proud of Polytechnique Montreal. I think you can see now that we're in good hands now with our chemical engineers. Remember that most of them are at the bachelor level or master level degree. So still, we have opportunities to progress and to evolve in something even greater. So thank you so much, everyone. You represented your school really well, and that was super important for me. So I would say this is the time for lunch. Thank you so much, everyone, and we'll meet again in the afternoon. I have an hour presentation on for you to show you how to use correctly computational thermochemistry. And don't hesitate to comment and to provide your feedback to the student. I think they did well, and you should encourage them for the future. So thank you, everyone.
So during lunch, I might